In this video, we're going to focus on nucleophilic substitution reactions. There's two common types that you need to know, the SN1 reaction and the SN2 reaction. But let's begin our discussion with the SN2 reaction. This is a second-order nucleophilic substitution reaction. The rate of the reaction depends on the concentration of the substrate, and it depends on the concentration of the nucleophile. It's first order with respect to the substrate, and first order with respect to the nucleophile, but it's second order overall. That's why it's an SN2 reaction. 1 plus 1 is 2. If you double the concentration of the substrate, the rate will double. If you double the concentration of the nucleophile, the rate will double. If you triple the concentration of the substrate, the rate is going to triple. If you quadruple the rate of the nucleophile, the rate will quadruple. What's going to happen if you double the concentration of the substrate and triple the concentration of the nucleophile? In that case, the rate is going to increase by a factor of 6. If you triple the concentration of the substrate, quadruple the rate of the nucleophile, the rate will increase by a factor of 3 times 4, which is 12. So what exactly is the substrate? Well, the substrate is basically an alkyl halide. So here we have 2-bromobutane. And we're going to add a nucleophile. Let's use iodide. Iodide is a good nucleophile. And in this reaction, iodide will attack the carbon from the back, expelling the bromide leaving group. The SN1 reaction occurs in a single step. It's a concerted reaction mechanism. All bond-breaking processes and bond-forming processes occur at the same time. Now, this reaction occurs with inversion of stereochemistry. The bromine was in the front, but now the iodide is in the back since it attacked the carbon from the back. So let's find out what the configuration was before. If Br is in the front, H is in the back. So let's assign Br a value of 1, the ethyl group 2, methyl 3, H is 4. So if we count from 1, 2 to 3, we can see that we have, this is going clockwise, so we have the R isomer. Therefore, the product is the S isomer. The hydrogen is now in the front, and if you count it, it's 1, 2, 3. It appears to be R, but because hydrogen's in the front, you have to reverse it, so it's S. So the configuration of the chiral center, it reverses in the SN2 reaction. As you can see, no carbocations were formed, and therefore the SN2 reaction is not subjected to carbocation rearrangements. Wherever the leaving group was located, the nucleophile is going to be on that same carbon. Now, why is it called a nucleophilic substitution reaction? As you can see, the leaving group was replaced or substituted with a nucleophile, and so it's called the nucleophilic substitution reaction. Now, SN2 reactions, do they prefer primary substrates or tertiary substrates? It turns out that an SN2 reaction works best with a methyl substrate. It's most reactive with these. And then it works well for primary substrates as well, but for methyl substrates it's better. And it doesn't work very well for tertiary substrate. Now let's compare a methyl substrate with a tertiary substrate. Let's see why. So here we have methyl bromide. And we're going to draw also tert-butyl bromide. Let's use hydroxide as a nucleophile. Now, if you react hydroxide with methyl bromide, it's going to be an SN2 reaction, and it works pretty well. But if you try to react hydroxide with tert-butyl bromide, it doesn't work well. Why do you think that's the case? Why does the first reaction work very well, but the second one does not work very well for an SN2 reaction? In order for the hydroxide to react with the carbon atom or with the methyl bromide, it has to attack the carbon so it can expel the bromine atom. In order for it to do that, the carbon has to be accessible. Hydroxide has a difficult time getting to this carbon because of these bulky methyl groups. The methyl groups they basically protect this carbon atom from the hydroxide group. And so because of steric factors, it's very difficult for hydroxide to access the carbon. And that's why tertiary substrates don't work very well. The carbon atom that has the leaving group is virtually inaccessible. It's very difficult to get to. So the SN2 reaction for a tertiary substrate is very, 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 very slow. So basically, it's almost non-existent. So SN2 reactions work well whenever you have an unhindered substrate or an accessible carbon atom to attack. Now let's talk about the mechanism of a SN1 reaction. So let's say we have tert-butyl bromide, and we're going to react it with a negatively charged nucleophile. Let's use iodide again. So the first thing that happens is the leaving group leaves. You have the formation of a carbocation. Now at this point, carbocation rearrangements can occur, but there's not going to be any rearrangements in this particular structure because the plus charge is on a tertiary carbon. Tertiary carbocations are more stable than secondary and primary ones. So after the carbocation is formed, the nucleophile attacks it. And so in this case, we get tert-butyl iodide. So if you have a negatively charged nucleophile, the SN1 reaction occurs in 2 steps. The rate of an SN1 reaction is equal to the concentration of the substrate times K. It doesn't depend on the concentration of the nucleophile, because the first step is rate limited. The slow step is the formation of the carbocation. It takes a long time to produce this carbocation. The second step, the combination of these 2 ions, is pretty fast. So that's why SN1 reactions are known as first order nucleophilic substitution reactions. Overall, it's first order. Now what if we have an SN1 reaction where the nucleophile is not negatively charged? It's neutral. In this case, the nucleophile is also the solvent. Whenever the nucleophile is the solvent, you have a solvolysis reaction. So in the first step, the leaving group is going to leave. And so we're going to get a secondary carbocation, which will not rearrange, and water, the nucleophile, can attack it from the back, or it can attack it from the front. So because it can approach the carbocation from both sides, we're going to get a racemic mixture. If it attacks it from the back, like the SN2 reaction, this is going to produce the inverted product. We'll talk about the final product, which is an OH, but I'll show you how to get there soon. So the inverted product will look like this. If it attacks, let's say, from the front, then we're going to get the retention product. Now keep in mind, this is not an equal racemic mixture. We don't get 50% R, 50% S. Rather, it's more like 60-40 / 70-30. We get more of the inverted product than the retention product. And the reason why that's the case is because there's a bromide ion that, even though it's disassociated from the carbocation, it's not always very far from it. So the oxygen of water has a partial negative charge. Bromide has a negative charge. So if water attacks from the front, as you can see, it's going to be repelled by the bromide ion. And so it's less likely to attack from the front. But if it comes from the back, there's no such repulsion. In fact, it's attracted to the carbon in the back because the carbon has a partial positive charge. In fact, well, it has more than a partial positive charge. Once the bromide leaves, it has a positive charge. So it's definitely want to attack it from the back. We don't have the influence of this bromide ion repelling the water molecule. So that's why the inverted product is still slightly more than the retention product. Bromide doesn't block access from the back, it blocks it from the front. But now let's finish the mechanism. So let's say water attacks it from the back. Initially, we're going to get a product that looks like this. Whenever oxygen has 3 bonds, it has a plus charge. And then we need to use another water molecule to get rid of this hydrogen, giving us the alcohol. So whenever you use a neutral nucleophile, the SN1 reaction will occur in 3 steps. If you use a negatively charged nucleophile, it will happen in 2 steps. The third step involves the removal of this hydrogen. Now, what about the substrate? We said that for an SN2 reaction, it works better if you have a methyl or primary substrate because the carbon atom is more accessible. But what about for an SN1 reaction? What's the case here? For an SN1 reaction, tertiary alkyl halides or tertiary substrates work better than secondary ones. Methyl substrates don't work very well. Now, why is that the case? Now, if you recall, the rate limiting step, the slow step, is the formation of the carbocation intermediate. To increase the rate of that first step, you need a more stable carbocation. It's very difficult to form an unstable carbocation, but it's easier to form a stable carbocation. And because tertiary carbocations are more stable than secondary carbocations due to hyperconjugation and the inductive effect, tertiary substrates work better for an SN1 reaction than secondary substrates. So methyl substrates are the least stable because the methyl carbocations are, let me take that back. Methyl substrates do not work well for an SN1 reactions because the methyl substrates are the least stable. So that's what I wanted to say. And so that's it. That's why tertiary alkyl halides work better for an SN1 reaction, is because the tertiary carbocation is fairly stable compared to the other carbocations. Now let's work on some more SN1 reactions. And let's focus on rearrangements. Let's not worry about the stereochemistry of the reaction. So let's say if we have 2-bromo, 3-methyl butane, and we're going to react it with methanol. If we use water, water is going to produce an alcohol. If you react an alkyl halide with an alcohol, for the SN1 product, you'll get an ether. But let's propose a mechanism for this process. So the first step in an SN1 reaction is the formation of the carbocation intermediate. So the leaving group have to leave, and we're going to get a secondary carbocation. The reason why this carbocation is secondary is because the carbon that bears the positive charge is attached to 2 other carbon atoms. Now notice that the secondary carbocation is adjacent to a tertiary carbon. And we know tertiary carbocations are more stable than secondary ones. So there's going to be a rearrangement, a hydride shift. That plus charge wants to be on the tertiary carbon and not on the secondary one. So this hydride is going to glide towards the plus charge. And basically, they're going to trade places. And so now, the plus charge is on the tertiary carbon, and the hydrogen is now on the secondary one. But we don't need to show the hydrogen. At this point, methanol, which has a partial negative charge on the oxygen, is attracted to the carbocation. And so it's going to attack the carbon with the plus charge. And so we have an intermediate that looks like this. Since we have a neutral nucleophile, the reaction will at least take 3 steps to occur. But because of the carbocation rearrangement, there's 4 steps in this reaction. Now, once we form this intermediate, we're going to use another methanol molecule to get rid of the hydrogen. And so now we have the final product, which is an ether. Notice that this carbon atom is not chiral. We have 2 methyl groups. In order for a carbon atom to be chiral, it has to have 4 different groups. So this is the product. You do not need to indicate stereochemistry for this product. In fact, you can't, because this carbon atom is not chiral. So the product is an ether. Now let's try another example. By the way, if you want to find more examples on SN1 and SN2 reactions, There's a lot of other videos I've created. Check out my channel. There's one where it's basically a practice test of 75 multiple choice questions. I created it a while ago, but if you type it in, like do a search on YouTube, you should find it, and you can get a lot of practice on these types of problems. So hopefully if you watch that video, it might be very useful to you. So let's say if we have an intermediate that looks like this. And we're going to use water in this case. So we have a secondary alkyl halide with a protic solvent, and this is going to favor an SN1 reaction. By the way, protic solvents favor SN1 reactions. Polar aprotic solvents favor SN2 reactions. But let's propose a mechanism for this reaction. So we know that the bromine atom is going to leave. This is going to produce a secondary carbocation. Now, this secondary carbocation is adjacent to a quaternary carbon, which contains no hydrogen atoms. So there's going to be a carbocation rearrangement, but it's not going to be a hydride shift. Instead, it's going to be a methyl shift. The methyl is going to trade places with the positive charge. And this time, we need to show the methyl. It's not a hydrogen atom that we can ignore. So now the plus charge is now on a tertiary carbocation, or a tertiary carbon, I should say. So now we can use water to react with the carbocation. Let's not worry about stereochemistry in this example. So we're going to have this intermediate, and then the last step is to take off the hydrogen. So this is going to give us an alcohol that looks like this. So this is the product. Now, if we decide to take stereochemistry into account, do we get one product or two products? Do we need to show the stereoisomers? So look at your final product. Determine if the carbon that has the OH, if it's chiral or achiral. So we have a methyl group. Here we have a secondary carbon and a tertiary carbon. So this carbon, the chiral carbon, has 1, 2, and the left side is different from the right side because these two carbon atoms are different. So it has 4 different groups. So the carbon atom is chiral, which means that the product consists of 2 stereoisomers. The OH can be in the front, or it can be in the back.